Welcome back. Um, so I'm going to start by presenting a fact, and then we're going to use it. Um, this is the general continuity properties. If two functions are continuous on the same interval, then their sum, their difference, and their product will also be continuous on the same interval. If two functions are continuous on the same interval, then their sum, difference, and product will also be continuous on that interval. How about the quotient of the two functions? Well, the quotient of the two functions will also be continuous on that interval, uh, except where the denominator is 0. So 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 that so if two functions are continuous, their quotient would be continuous on the same interval, except for values of x that make the denominator 0. Okay, so if I apply if well, we know this fact already, that the polynomial functions are continuous for all values of x, because we know that the limit of a polynomial at any point is given by the value of the polynomial at that point. And then number two, rational functions are continuous for all x except those values that make the denominator 0. And this is where we are applying the fact here that the quotient is continuous wherever the numerator and the wherever both the numerator and the denominator are continuous, except where the denominator is 0. So for a rational function, then it's the ratio of two polynomials. So for a rational function, both the numerator and the denominator are continuous on the entire set of real numbers. So a rational function will be continuous everywhere except where the denominator is 0. So property number fact number 3 here is that the nth root of a function f is continuous wherever the function f is continuous. So this is when n is an odd positive integer. So if n is an odd positive integer, then the nth root of f is continuous wherever f is. But if n is an even positive integer, then the nth root of f is continuous everywhere. Is continuous wherever f is and f is positive. So when n is even, then we need to make sure that f is also even. For the nth root of f to be so if n is even, then for the nth root of f to be continuous, we need the nth root of f would be continuous wherever f is continuous and f is non-negative. Okay, so here's here's our first example. So let's say f of x is this rational function. Well, notice that the numerator and the denominator, they are both polynomials, so they are both the numerator and the denominator are continuous everywhere on the entire set of real numbers. So this rational function will be discontinuous only at values of x for which the denominator is 0. So let's figure out where the denominator would be 0. The denominator would be 0 when x is 2 or negative 3. So this function has discontinuities when x is 2 or negative 3. and so f is continuous. So notice that it is f is discontinuous only at -3 and 2, but it is continuous everywhere else on the number line. So f is continuous from -infinity to -3, union -3 to 2, union 2 to infinity. We are using open parentheses at 2 and -3 because those two are not included in this interval. G of x is root of x minus 2, and so as we the facts that we presented earlier tells us that this is an even root, so to this even root would be continuous wherever the quantity inside is continuous and positive. Well, the quantity inside is continuous everywhere because it's a polynomial, but let's see where it is positive though. It is positive only when x is bigger than 4. So as a result, this function g would be continuous on the interval from 4 to infinity. Now I am including 4 here, but let's realize the fact that if you look at the graph of this function, the graph starts at the point 4, 0, and then it extends to the right of 4. So there is no left-hand limit at 4, or there is the two-sided limit at 4 is not defined. However, the limit at 4 from the right side is defined and is equal to the value of the function. So in this case, we say that this function g is continuous at 4 from the right side. So that's why I'm including 4. H of x is the fifth root of x cubed plus 7. Once again, this is an odd root, so an odd root function is continuous wherever the quantity inside the root is continuous, and the quantity inside the root is a polynomial, so it's continuous everywhere. So the odd root here would be continuous for all values of x. So it's continuous on the interval from -infinity to infinity. We want to find all points of discontinuity of each function. So in this case, it's a rational function, so we know that the discontinuities would be where the denominator is 0. Well, the denominator would be 0 when x squared minus 1 is 0, or when x squared is equal to 1, and that means that x is plus or minus 1. So we see that f is discontinuous when x is 1 or minus 1. How about the function g of x, which is defined piecewise? When x is bigger than or equal to 2, the value of g of x is x minus 3. When x is less than 2, it's strictly less than 2, the value of the function g is 3 minus 2x. The domain of g is the set of all real numbers. Notice that g of 2 is going to be minus 1. So 2 means we are in the first formula, so g of 2 is -1. Now, notice that right at 2, the formula for the function changes. So we need to figure out what's going on at 2. But if you look at when x is strictly less than 2, the function g is a polynomial, so there. So since it's a polynomial on the left of 2, it's got to be continuous there. When x is strictly bigger than 2, the function is given by a polynomial, so it's going to be continuous. G would be continuous when x is strictly bigger than 2. But right at 2, since the formula changes, then we need to figure out whether it's continuous or not at 2. To do that, we want to look at the limit at 2. So let's look at the limit at 2. The limit at 2 from the right is, if we are going to 2 from the right, that means x is bigger than 2. In that case, the formula for the function g is x minus 3, and as a result, we get the limit to be -1. What's the limit at 2 from the left? Well, from the left, x is less than 2. So now the function g is equal to 3 minus 2x, which means the limit is 3 minus 2 times 2, which is negative 1. So we see that the right and the left hand limits are equal. So the two-sided limit at 2 is equal to negative 1, which is the same as g of 2. So we see that g is continuous at 2. So therefore g has no discontinuities. Okay, so I am going to stop the video here, and I will see you soon in the next video.